Okay folks, today I want to chat with you about a topic of interest to me, has been for quite a while. Call this a driver alignment. So I want to explain to you all what driver alignment's all about, why it's important, and then I want to chat with you all about what I learned this past winter as I came up with a means to actually measure driver alignment and discovered some very interesting things I want to share with you all. So first of all, we need to talk about what driver alignment is. So, well, driver alignment is an issue only related to having two very different kinds of drivers in a speaker system. So in an ideal world, we might have just one driver that produces all of the frequencies, and we don't need two different drivers. But that doesn't turn out to be the case. Drivers are very difficult to manufacture to do the full range. There are some Fostex drivers that are claimed to be full range. They probably do well up to about 10,000 cycles, but they're probably good for computer, little speaker monitor kinds of things, but not for high fidelity music reproduction. For that, you're not going to get real good high end out of a mid-range driver. You've got to incorporate a tweeter with a specialized, in this case, a fabric dome, and I like metal dome tweeters, but whatever, we have a specialized tweeter to handle the high end and a driver for the mid-range, and then of course there'd be a driver for the bass. Well, so let's just talk about getting two drivers to work together. Drivers will incorporate a crossover to filter out to isolate the highs from the mid-range driver and the mids from the tweeter. And so in an ideal world, say if the crossover were 3,000 cycles, we would have a complete drop-off of any reproduction of sound from this driver at 3,000, and the tweeter would take over completely. Hence, the tweeter going down, the tweeter would stop reproducing everything at 3,000 cycles. But that, of course, is not the way it works. We're using analog circuitry in which we have a capacitor and a coil, or pairs of capacitors and coils. In the passive side, at least, or even on the active side, if you have separate amplifiers and you have an active crossover, you're going to filter these out through an analog circuit, and it means that the mid-range driver at the crossover point will gradually decrease in amplitude as you go up, and the tweeter likewise will gradually decrease in amplitude as you go down below that crossover point. So there's going to be a band pass between these two drivers, a range of frequencies in which both drivers operate. And so that is the rub, because when you have two drivers operating at the same time, there are some potential problems. One, of course, is that you have different kinds of diaphragm materials producing the same frequencies. It's not really ideal, but there's no real way around that. Well, there's another issue of importance that many folks have taken an interest in trying to compensate for, and that we call driver alignment. So what is alignment all about? Let me compare, if I might, if we were to consider using two of the same kinds of drivers, what would be the case? If both drivers were operating at 3,000 cycles going, and I'm going to move these slow, these are burned out drivers, so I can yank on these, but if these were going back and forth, you can see that they would both produce waves at the same time, but the important matter would be that in this plane, the center of this wave would be located perhaps as close to this convex center cone here, center of the cone, and that center location would be the same for this driver as for this driver. So as these produce waves going back and forth simultaneously as they would be in phase, right? They would produce at some position out here, the wave would arrive at the listener. Suppose your listener is standing here, the wave would arrive at that listening position at the same time. But if we use a specialized, different kind of driver, this tweeter, the problem then is that the center location of this, the 3,000 cycle frequency for this driver is back here, and the location of this one is forward. And so the wave from the tweeter is going to arrive at this listener position a bit sooner than the wave from this driver. Hence the waves would be out of phase. Now if they're out of phase by just a little bit, then that's not going to really be an issue. But if they're out of phase by 180 degrees, then you're going to have let me demonstrate with these two drivers again what a 180 degree out of phase condition might look like, because I can actually physically move these. So an out of phase condition might be if this one is producing the positive wave, this one I pulled apart. This is producing the positive wave, this would be doing the negative. And so they might go back and forth like this. Well, that is to say, let's do it in a more realistic way. Suppose this one's out here, they both produce a positive and negative, but by the time in any position here, by the time the positive wave gets from this driver gets to the listener position, the negative wave has arrived at the same time. And so the negative wave cancels out the positive wave, or that is, both waves cancel one another out. And so from the position of the listener standing here listening to these two speakers, you would have a cancellation going on. Now that would not be a problem if you have identical drivers and they're sitting on the same plane in phase, but if you have different kinds of drivers, as is the case here, and the tweeter is forward of the mid-range driver as far as its central location of waves, then that wave could be arriving sooner than the wave of the mid-range driver, and then by the time they both get to the listener, they've canceled one another out. At least that's potentially what could be happening. They could be 180 degrees out of phase and cause cancellation. Some of the techniques been involved in designing speakers has been to, in some ways, mount this tweeter back. As I show it here, there would be a single baffle plate here. Both these drivers would be mounted onto, which would be commonly the case. But that runs the tweeter forward of the mid-range driver, at least as far as the center source of the waves. So there have been tweeters that have been designed with a somewhat of a concave faceplate that physically locates the cone of that driver back a little bit. So let me talk about some of the issues involved first. We want to consider, first of all, what is the length of the wave at, say, let's say 2,000 cycles. I did that with my 8-inch two-way that we're listening to now. I use the 2,000 cycle frequency, crossover frequency. So what is the length of the wave at 2,000 cycles? Well, if I can show you this, this is a 4-inch and this is 3/7. So the wave is about this long, about 6 3/4. I'm just using the drivers as a reference point because I know this is about, well, it's about 5. So yeah, so maybe the wave is about 6 1/3. So it's about this long, the length of the wave. So now actually I should do it this way. The length of that wave is way out here. And so this small amount is not going to produce a 180 degree out of phase condition, is it? So that's not really the problem. Now at 3,000 cycles, the wave is a bit shorter. I don't remember the exact figure, but it's shorter than 5 inches, something like 4.5 or something, but still, that would mean these drivers would have to be off by 2 inches in order to be out of phase, 180 degrees. At 3,000 cycles. And so if you had a 3,000 cycle crossover frequency, you'd have to have this driver out. There'd have to be a difference here of at least 2 inches to be out of phase, 180 degrees. And so from that standpoint, the whole driver alignment issue is of no concern at all. From the standpoint of the length of the wave and the position of these on a faceplate, you're only off by maybe, what, 3/4 of an inch? Not quite an inch here. Between here and here, you've got maybe, the tweeter is maybe forward of that mid-range driver by maybe 3/4 of an inch or something like that. So from the standpoint of the wavelength, I would say there's you're not going to have a 180 degree out of phase condition here. So that, from that standpoint, we would ignore a driver alignment in terms of at least physically trying to align this driver somehow. And that was what I was initially chasing after. I was going to physically align the driver, put the tweeter back here, get it, and measure it and get it so it's exactly it. The problem here doing this is that you have this interference of this step, whatever this step's going to be right here. And then you'd have to put this driver behind the front plate, cut a hole in it or something. That's kind of what I had in mind. Well, so from the standpoint of the wavelength, wavelengths at 2,000 or 3,000 cycles are too long to be of any concern as far as driver alignment. We're only going to be off by 3/4 of an inch here. We're talking waves 4.5, 5 and 6 over 6 inches long for 2,000 cycles. So it's of no concern there. Now, having said that, let me talk to you next about measuring the waves, because I actually did that right here on this desk. I took a single microphone and I sent the 2000 cycle wave, in this case for the 8-inch and the 2-way system, a 2000 cycle wave to the mid-range driver. You could have sent the 3000 for these. And first of all, and this was an electronic crossover, so I had just this amplifier working. I turned this other amplifier off. So this microphone just picked up the waves from this one. Now those waves were recorded into Cubase, and they were sitting on the timeline in Cubase. And so when I played it back and then recorded it on another track, the recorded track, the source track and the recorded track are exactly lined up, so I could tell how. Well, now I wasn't concerned about the source track versus the recorded track, but I was concerned, since the source track did not move along the timeline, that this recorded track of this driver and the recorded track of that driver would be lined up relative to the source track, so that I could compare the two recorded tracks and see if they were in fact in alignment. And that is, I can take in Cubase any point along the recorded tracks, and I can open that or expand those tracks out so that I can actually see the waves on the track. And I can see the top one and I can see the bottom one. That is, I could see the waves from the mid-range driver and then to see the recorded waves from the tweeter and see if they actually line up or if they're out of phase. And so what I discovered was that the tweeter was nearly, not exactly, but nearly 180 degrees out of phase. And it wasn't due to the length of the wave. The length of the wave is only if that was at 2,000 cycles, the length of the wave is over 6 inches, here, about this long, or like out here. And yet the tweeters are only misaligned by just 3/4 of an inch at best. So how could I explain why the tweeter was giving me an 180 degree out of phase condition? I checked the phasing of the connections. You have speaker leads. These are broken. This is a broken tweeter, but I checked the speaker leads to make sure I had them connected properly. These are broken drivers, don't worry about it, but there's a positive and a negative, and you get those reversed, and you'll have your polarity reversed, you'll have an out of phase condition that way. So I thought maybe I had the polarity reversed on the tweeter at some point along the path, signal path from the signal source going in was probably in phase, but maybe coming out of the amp, I had the wires backwards, and I had this tweeter was out of phase 180 degrees, and the alignment, the phasing was correct. So I had a problem. How do I explain how the tweeter was out 180 degrees out based compared to the mid-range driver? By the way, I did check my testing procedure, and the way I did that was I took the mid-range driver and measured it, and then I sent the tweeter signal into the same mid-range driver. So I checked the low-mid frequency path, signal path, and then the tweeter frequency path. And I determined that those two waves, when I recorded them, they were dead on aligned. So I know my testing procedure was correct. So there was some mysterious reason for why, when I measure the two drivers, I find that the tweeter is out by not exactly, but nearly 180 degrees out of phase, which is your problem scenario, right? If it's off by 10, 15, 25 degrees, who cares? But when it's 180 degrees out of phase, it's exactly, it'll cancel each other out. That's the problem. The one wave, as I mentioned earlier, will cancel the other out. So why is that? Why was it so far out of phase? And I thought about it for quite a while, and I came up with what I think is the reason. Okay, to help understand what's going on, I've gone ahead and taken these drivers apart to show you, and it should be obvious without taking them apart, but I'm going to take these apart and show you anyway, that what we see here is the driver element for the bass mid driver, or this mid-range driver, compared to the size of the element for the tweeter. And what we immediately see is that the amount of mass and weight involved in this diaphragm is far greater than this one. And that should be obvious. Well, there's a second matter obvious also. This driver has a single, let me get this in focus. This driver has just a single surround attached to the voice coil right? That's the nature of the design of a tweeter. Whereas this cone has actually has a rubber surround on the outside, and then it has a spider here. I've cut this, but this spider was attached to the frame. You can see that inside the frame here. This is the remaining of that spider that I cut out. It was glued here. But this spider is also holding the voice coil centered. And so because of the size of this cone, you need two places where this is being held, where this cone is being held in place. Whereas a tweeter, again, only has the one surround here that holds it in place. So this driver has to not only move a whole lot more mass when it goes up and down, but it has the resistance of both the inner spider and the outer surround to work against. So if we now think about these two drivers sitting here with the voice coils exposed, and we imagine a voltage going to this driver and around the coil and producing a magnetic field, which then of course has to act against the permanent magnet that it sits in. So yeah, it sits inside there, right? It doesn't fit in there anymore. It's got a bunch of mess in there, but it has to operate against, it creates a magnetic field that pushes against or pulls on the permanent magnetic field of the permanent magnet. And so when you put a voltage across that, it has to get this cone moving. And that's an awful lot of weight to get moving. Now, it's not going to take a half a second to move, right? It's going to be moved pretty quickly. But when you compare how much faster it would get moving with all that mass having to go up and down compared to the tweeter element that's I mean, they're both only going to move just a tiny little bit, but this tweeter has far less mass to deal with to move up and down. And so when you put a voltage to this coil and you ask it to move, it can move pretty quickly because it's very, very small and light. It's only got a little bit of resistance to it. This one's got a great deal more resistance, both mass and the two mounting components that hold it in place. It has a lot of resistance to overcome and a lot of mass to move. So it's a very simple matter when we're talking a thousandth of a second. And by the way, half a wave off is only a quarter of a millisecond, and so millisecond is 1,000th of a second. So half of that. I'm sorry, it was a quarter of a millisecond. So, in other words, the tweeter only has to get moving a quarter of a millisecond faster than the mid-range cone in order to produce a 180-degree out-of-phase condition. And that, in fact, was happening. Now, I don't know if it was only a quarter of a millisecond. I know it was off by a half a wave, 180 degrees out of phase, or a half a wave. Whether it was wave and a half, 2.5, 3.5 waves, I can't tell. And further testing might have helped if I had the right equipment to do that. But nonetheless, it didn't really matter. The idea was that the physical alignment of the drivers was not the primary factor. Even the fact that the wavelength is so much greater compared to the positioning of these, that isn't even a major concern. The issue is the tweeter has so much less mass to get moving. It can move and produce its wave up, and I'm moving it up and down to demonstrate that, so much faster than this mid-range driver, because it simply has so much more mass to move. And so at the millisecond range, this driver is just going to take a little bit longer to move than this one, and it means that this driver will move potentially out of phase. And I'm exaggerating the amount of movement, of course, here with my hands, but this tweeter is going to will move that much faster because it's lower mass, and so you'll have this out of phase condition. And how you can tell that? Every tweeter is going to be a little different, act a little different, and have a different phasing condition. I measured a couple of other tweeters, and they were all off by some significant amount, but by different amounts. And so tweeters aren't all the same. The amount of mass involved here, the amount of resistance based on the kind of surround the tweeter uses and all that. And of course, what the kind of mid-range you're comparing it to. Its mass, its cone material, it's the resistance of the surround and the spider. All are going to be factors and are going to affect the phasing alignment. So that was my conclusion based on my scanning, that simply the difference in mass and other resistance factors are what's creating out of phase or alignment issues for a bass mid driver versus a tweeter. So it has nothing to do with the length of the wave. It doesn't have anything to do with positioning. The drivers aren't relevant. The most relevant factor is simply the difference in the amount of mass of the different kind of drivers. So that's my conclusion on alignment and how you measure that. Well, I have in my electronic crossover that I built for the Triamp system that I got to do a video on one day. I have an electronic delay circuit that Phil Marchin built for me that I included in line with the mid-range crossover, which has an adjustment on it, and I can delay the waves going to the mid-range driver by an adjustable amount, and I was able to use that to align these. If I can delay this one a little bit, then if they're out of phase, I can just correct them so they're now in phase as they go back and forth. So that's probably the ultimate solution, and probably the only reasonable solution, is an electronic delay circuit that's adjustable. But then you have to have a measuring system, and I was using, again, Cubase and recording the signals. That's quite complex for the ordinary builder, so I'm not sure if this helps the builder at all, but I wanted to explain it all, so if you have a buy speakers or if you concern yourself with alignment. Having said all that, did it really make an audible difference in the system that was 180 degrees out of phase? I tried it it was about 180 out. And I could reverse the polarity of the tweeter in this case for my active two-way system, which I don't have a delay circuit in. I'm not going to go to that trouble. But they were off by 180 degrees, and so I reversed the polarity of the tweeter and I got them in phase. Did it make an audible difference? I got to be honest, I couldn't tell. So a whole lot of huff and puff about driver alignment, and the matter is much more complicated, having to do with driver mass more than anything else, and how to correct for that. It's not simply a matter of figuring out physically positioning the drivers. And so I learned all that last winter and wanted to share that with you.